Well, welcome everyone to another session of Quantum Computing, Chicago, Illinois, and beyond. Tonight's presentation on quantum resistance and the Internet of Things, brought to you by Charles W. Clark, who is associated with the Joint Quantum Institute of the National Institute of Standards and Technology. Sounds like NIST. And the University of Maryland and Science Cast In. So, Charles, if you want to pop up and introduce yourself, that would be great.
Well, my name is Charles Clark. I'm a theoretical physicist by training, but I interact a lot with experimental groups, and I've been active in quantum computing and communication from very early days, mid 1990s. And today I'm going to give you a relatively non-technical presentation of some of the issues associated with data security and quantum encryption. And when I say relatively non-technical, I think we're limited to things like binary arithmetic of zeros and ones and parallel and serial electric circuits. So there's not going to be any heavy math. Oh, and states of polarization of light. There's not going to be, it's basically conceptual. And I think from my experience of giving this presentation before, should be generally accessible to a technical audience. That is, someone with a bachelor's, some equivalent of bachelor's degree in science and engineering. So may I start? Are there any
Please do.
questions?
I have a question, Charles. My name is Messiah Moody. I am a machine learning engineer, and I just wanted to know if do you have any papers that you would recommend, either now or
Yes, I will show quite a few original papers that are, the full bibliographical information is visible. So just please shout out when those come up on the screen and ask me to pause. And those papers will be visible in the recording as well. That's a
Okay,
very good question.
and Charles, you're okay with interruptions during your presentation,
Of
or do you
course,
want
of
to?
course.
Okay, perfect. Well, if you want to, you have a presentation, you want to do a screen share, give it a
I do.
shot. There we go.
Let's see.
And I'm seeing what looks like a desktop, so I think we're
So
start.
let me make this my active screen. Right, quantum resistance and the Internet of Things. So here's a World War II poster about the problem of the world listening and the need to keep communications secure during wartime. So I'm going to start with here's a report from the South China Morning Post, newspaper published in Hong Kong, from a little bit more than a year ago. China and Russia test hack-proof quantum communication link for BRICS countries. Any voices from the audience on what BRICS countries are? Well, this is the BRICS homepage. It's a coalition of states. The founders are Brazil, Russia, India, China, South Africa. The other members you can see here, and the partner states. And it is, with the exception of Brazil and South Africa and some of the African countries, it's largely a Eurasian consortium. So here's a conventional picture of the continent Eurasia, consisting of Europe, Asia, and Middle East, and the Malay archipelago. And this report of the South China Morning Post concerned a paper that was published in Optics Express, which is very good journal of Optica Worldwide, formerly known as the Optical Society of America, just about a year ago, 25th of March, 2024. Eurasian scale experimental satellite-based quantum key distribution with detector efficiency mismatch analysis. The co-authors are all from Russia, and we'll see exactly what was done in this experiment in just a few slides. But before going there, let's just look at the concept of Eurasia. So here's a paper that's famous in geography for articulating Eurasia as sort of the center of the world. Now, it may seem odd to think about Chicago as being on the peripheral of the world. I lived in Chicago for 5 years as a graduate student. I thought it was the greatest city in the world. But if you look where all the trouble starts, it's typically in these, here's this pivot. It's a large land area, so it allows transport of military forces over vast distances. And it has been the scene of most of the great wars in the world. This paper was published in 1904, 10 years before the start of the Great War, which was a contest between basically 5 empires over the distribution of power in this central pivot. And so the Eurasian name of this exercise harkens back to concepts like that. Now, what was done here in this experiment, it was a transmission of a message between a place in China with Nanshan and a place in Russia, Zvenigorod. And these are two towns or cities with very highly capable telescope stations for looking at satellites. Would anyone like to guess at the purpose of such stations? High-powered telescopes in the interior of a country, which are not dedicated to astronomical observations, but for communications with satellites.
Are they reading the entangled photons from the satellite?
Well, yes, these are, but they weren't built for that purpose. They were built many years ago for a completely different purpose. So yes, they've been deployed for that. But the thing is, these are facilities that have high capital value and operational costs. They exist for another reason.
Spy planes?
Who would like to?
Is it research purposes?
I doubt it. The United States also has a large number of such stations. So they're basically they're observing orbit to discover orbiting craft that they don't know about. So, for example, when China or Russia launches a satellite, they typically don't broadcast it in the newspapers. Or when we do it, the United States does, we don't broadcast it in the newspapers. But many other countries are actually interested in what's up there. And I think the original motivation for this is something like defense against aerial attack. So there's a very powerful such station in Hawaii, which is operated by the Air Force, which is used basically to keep track of things flying at very high altitudes or low orbit. So there's infrastructure available for this type of experimentation in the major nations of the world. We'll see more about the Chinese the Chinese capability later on the talk. So what this what was done here is a very simple type of encryption. Well, it's mediated by quantum mechanics, so we'll get to that later. But basically, there was a message that was encoded in China. It's a graphical message. So in other words, here is there's an exchange of images. So here is the original image, a quote by a Chinese philosopher, which had its bitmapped version, its two-dimensional bitmap version, encrypted, is seen here. And then here is the corresponding Russian message, which is a quantum mechanics formula due to Landau, and its encrypted form. And we'll see more examples of this later. But basically, what was done was there was a upload of an encrypted message to the satellite in one station, download of the encrypted message the other station, and then there was a creation of a shared key that allowed the two counterparties to determine the message. That's more the detail that we'll discuss later. So I want to start with basic historical overview of the whole idea of secure encryption over insecure channels. This is very important. So when we say encryption, you might think of espionage and other nefarious activities. In fact, every time you order something from an internet merchant, or you access your bank account over the internet, or do any other type of exchange of sensitive information, it's not top secret, but you don't want your library card number to be published in the newspaper. You want to keep your banking and you want to keep your personal information secure from others. There's nothing paranoid about that. You take advantage of an incredible machinery which gives you a high degree of security against an interloper being able to read your message. So you're sending messages over the cell phone network. Well, those can be intercepted, but because they're encrypted in a very effective way, you don't take a big risk. So that has to do with the existence of so-called public key infrastructure, which has been a real gift to the world, in my opinion. And then recently, there's an emerging quantum threat to public key infrastructure. So we'll discuss the nature of that. There's one response to that is quantum cryptography of the type we've just seen, and we'll go a little bit deeper into that. And then there's a new modality of encryption called post-quantum encryption. That is a form of, it's an extension of existing public key infrastructure, but to use algorithms that are not known to be susceptible to quantum attack. And then for the kind of quantum physics portion of this, we'll just talk look at operations of very simple quantum random number generators, which I think are a good place to start. You want to study a quantum device that's relevant to these issues. My advice is to try to read some papers on quantum random number generation, and I'll show you some examples. Okay, so cryptography. Here is the entry on the word cryptography from the Oxford English Dictionary. The great virtue of the Oxford English Dictionary is that it defines words in terms of their historical usage. So cryptography, from crypto, secret, like a crypt, and graphy for writing, as in graphic novel, secret manner of writing, etc., etc., etc. First used by this genius, John Wilkins, published in 1641 in this book. Everyone should read this book. It is magnificent. It's available in a modern version. Mercury, the secret and swift messenger, showing how a man may, with privacy and speed, communicate his thoughts to a friend at any distance, by John Wilkins. Now, when I read this, I thought, wait a minute. When was this published? 1641. I mean, there wasn't any like radio or anything like that. In fact, there wasn't even a telegraph. I mean, the communication over a distance already, what channel would you use? Does anyone want to conjecture what the communications channel for communicating by a distance might have been in the year 1641?
Paper.
Well, okay, that's one way of doing it. But this discusses a form of communication that does not require the exchange of material objects. I mean, that is a modality, but
would it be flashes of light?
Yes, sir. So here's the in this book, he describes a mode of communication that was first presented by a man named Polybius in the 2nd century BC. It only works at night, but we'll see how it can be used in the daytime as well. Very ingenious. So you have two parties. We'll call them Bob and Alice, that have the same apparatus. It's two tables, each with 5 torches, lit torches, and this is being done at night. So they're standing maybe a kilometer apart, and so when they want to send this gives digitization of the communication. So in other words, the letters of the alphabet are described by the position of torches held in the left hand and in the right hand. So if I say here's the H, would be 2 torches held up in the left hand and 3 on the right. A would be 1 on the left and 1 on the right, and so on. So you encode the alphabet in the position of these torches. And then I think you can imagine in your mind, when you do this, I mean, you can actually do some interchange to establish agreement. And it's not all that sensitive to the position of the torches. There's some that are up and there's some that are down. But basically, a lot of the noise in the communication channels is just suppressed by the spatial variation of light sources, simple spatial variation of light source. Rather profound idea. And I think you're all familiar with this sort of arrangement here, the use of semaphores. Semaphore communications is still used in the United States Navy, not for conveyance of top secret information, but there are certain circumstances, like the approach of a ship towards a dock in harsh weather, where you want to have a message sent between two points that's clearly visible to a lot of people and not subject to radio interference. So by the motion of the hands, one can spell things out, and there can be regular communications. This mode is called the telegraph, an optical telegraph, the use of light signals to send written information graph over distances. And this was, a refined version. This was deployed in France by a system of towers with these adjustable vanes. Now, I don't know if you can see it in this picture, but here's one of these towers. It has these adjustable vanes. They're like the semaphore signals. So by an arrangement of there's an arrangement of the vanes that communicates a character message, And then off here in the distance, there's another such tower. Both towers have a set of vanes and a telescope. So they can send single characters. They can send a set of characters between each other. And in around 1800, there was a national network of these things in France that could relay a symbol from Paris to Lyon in 9 minutes. And that would be basically a day's journey by coach. In fact, the word telegraph comes from exactly this. For example, some of you may have visited San Francisco and been in Coit Tower on so-called Telegraph Hill. Well, it was called Telegraph Hill because at one time there was an observatory in this tower with a telescope that looked at flags on the mast of incoming ships coming into San Francisco Bay. And those flags on the mast would state the cargo the particular ships had. And then that would be recorded in Coit Tower. And they could send word down to merchants in the town of what was coming in to advise them of, when the latest goods were on sale. Very practical economic use. And this is not secure information. It's actually highly visible. So the question is, suppose you want to send a message over an open network like this, but send it in a way that doesn't reveal its content. Has anyone a suggestion for that? In other words, you're going to use alphanumeric characters, but you want their meaning to be apparent only to a particular destination of your choice or multiple destinations of your choice. Well, that's where encryption comes in. We'll get to that later. So in the fullness of time, the electric telegraph was invented, and it spread throughout the world very rapidly. Here's an indication of how that came to be in the context of the United States of America. So the electric telegraph, you're sending dots and you're sending signals in terms of a quick pulse and a long pulse, dots and dashes. Those are encoded into alphanumeric characters, and then you by tapping the keys, you get a quick tap for a dot, a tap with a short depression for a dash, and you can digitize any alphabetical signal and send it along an electrical wire. And in the United States, when the railroads were being built, I think anyone who's any adult in America has seen a picture something like this: a railroad track with a line along it, and this is a telegraph line. So with a train, you could easily erect a secure telegraph line. It's held off the ground, so it's not secure against deliberate attack, but it won't be accidentally disrupted by anything. And the train gives you a very easy way of finding faults and repairing them by setting up a new mast. And by 1891, there was actually a worldwide web of electrical telegraphs. There was a transatlantic telegraph, both in the North and South Atlantic, and all of Asia down into through Malaysia and into Australia was covered. There's a very wonderful book about this, The Victorian Internet, which actually describes things like dating services and so on. Many of the internet-based products that we know today had their first origin in similar things where the the communication was conducted by telegraph. So, TikTok wasn't possible then. You couldn't see videos, but it made possible a tremendous diffusion of knowledge. And
Charles, I have a question. What if there was an error in transmission or just in tapping out these signals? What happens then?
So I think in the first instance, so these signals wouldn't travel that far. Okay, they'd go for, I don't know what, 10 or 20 miles. So they needed to be repeated. You weren't transmitting directly from Vancouver to Sydney, but you were sending a message through multiple stations. So in a case like that, the message would be read, and then there would be a feedback loop where the intermediate station would test it for clarity. So I think there are other ways of doing this. There's I suppose like how the 8-bit error detection and correction in bit signals, you put on a few redundant bits that are basically a logical function of preceding bits. So I mean, we'll come to that later. I don't know how it was done in detail in those days, but certainly it was highly effective. Newspaper articles were transmitted by this technique. So I think they'd just be read on the other line, and there'd be a request for correction if there's any ambiguity. Well, all this, of course, disappeared when the telephone came into use. And so the bandwidth of a telephone is vastly superior to the electric telegraph. Okay, now, so I've alluded to the fact that you can use logical techniques for error detection and correction. And we're now going to come in to discuss the matter of keeping. So that provides a security of the information flow. And then there's a second aspect which is important, which is to communicate things in that form in a way that can only be understood by a particular recipient or a group of particular recipients. That is, in other words, if you want to send a social security number or bank account number, you're able to do so in a way that only the intended recipient can interpret it. So you're going to encrypt your data transmission. And the link between these is due, well, first of all, systematization of mathematical logic. George Boole and Augustus de Morgan were sort of the principal figures in the mid-19th century. And as for cryptography, the two great giants, and if you understand their work, you'll understand a lot about modern cryptography, are Gilbert Vernon and Claude Shannon, both employees of the Bell Telephone Company in the 20th century. So we're now just going to go through a little of the binary encoding and decoding of information. So in binary logic, you have basically a variable has two values, conventionally 0 and 1. And so here are some of the basic binary logic operations that you'll encounter when you first study this. A and B, so 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. A or B, this is like you can see this looks like multiplication. A or B, which looks like addition. 0 and 0 is 0. 0 plus 1 is 1. 1 plus 0 is 1. And 1 plus 1 is 1. And this is the most important construct in this simple class, the exclusive OR. So in the exclusive OR, the result is 0 if the two arguments are the same, and it's 1 in which the two arguments are different. And this maps on in a very natural way to the simplest type of electrical circuits. And it was Vernon's genius that led him to discover how this made it possible to do high-speed encryption over electrical networks. So this is what's, someone please say yes or no. This should be familiar to anyone who's taken a basic electronics course. You have a battery here, and you have two switches, and then you have a light emitting diode. Okay, so when either of these switches is open, no electric current can flow through the circuit. But when the circuit is closed, then current can flow, and you illuminate the LED. So this simple so-called series circuit, because the switches are in series, replicates the A or B, the OR operation. Is that clear? If not, you can think about this as a source of water flow, and these two things are sluices. So in order to get water to flow across this gap, you need to have both sluices closed, and then you'll get water there. Would someone like to suggest what the next type of electrical circuit that comes up in this construction is? Do we have like an electrical engineer in the audience? There's a series circuit, and then there's something else.
Series of circuits or connected circuits.
Well, let's say it's called the parallel circuit. So here the switches are in series, and here they're in parallel. This is a very, if you take an elementary electronics course, this is one of the first things you learn, because then you have to calculate the resistance, the impedance of circuits of this type. You typically break them down into series and parallel parts. So here's the OR, okay? So in this case, the two switches are in parallel. So if either one of them is closed, here's the one is closed, here the lower one is closed, here the upper one is closed, then electric current will go to light the bulb. Or if they're both closed. So it goes, this is the OR. If either A or B is set to 1, then the OR, the result is 1. Okay, now finally there's the XOR, or exclusive OR, which is this key tool of modern encryption. And so, I set this as a homework problem. Let me just show you the solution. It's quite similar to the OR. So in other words, you have in order to get current flow through the circuit, A and B have to both be closed. So and this is an arrangement that gives the following truth table. So in other words, if A and B have the same value, the result is 0. If it's different, the result is 1. So here is a patent, 1919 patent by Gilbert Vernon, which has been called by the National Security Agency one of the most important patents in the development of encryption. And the basic idea is as follows. You have two partners to the communication. In the literature of cryptography, these are often called Alice and Bob. And here's a simple communications protocol. Alice has a message. It describes, let's say, a bank account number, and the message is expressed in binary notations. So I think, can you see that? How 1, 2, 3, 4, 5, 6, 7, 8. This is 8 bits, and I think most of you who work with like ASCII character representation will realize that 8 bits can describe virtually all the symbols that we use in ordinary written communication. So here's 1 byte. It might correspond, I don't know what, to the letter C or something. And Alice wants to send that message M to Bob, but she wants to encrypt it. That is, she wants to disguise the contents of the message in a way that Bob can interpret, and only Bob can interpret. So the way that is done in Vernon encryption is that there is a shared key. That is, Alice and Bob have previously agreed on the same set of characters which are going to be used to encrypt this message. And the encryption is done, the ciphertext is the text that's going to be sent over the public channel. And this is the important thing. You always want to use a public channel to communicate. A simple version of this is you can send a secret message by purchasing a want ad in a newspaper that's printed, and everyone in the city can see the message that you wish to send, but you've encrypted it so that only people who have the key to decipher the message can actually understand it. In fact, that's, when you purchase something from Amazon, that effectively is what happens to you. It's in a much more elaborate version of this, but it's the same idea. So in other words, Alice does the exclusive OR of the message with the key to create the ciphertext. And when it's sent, here's the ciphertext. It's sent over a publicly accessible network. It might be printed in the newspaper. It might be sounded by a car horn. The security of the transmission channel is irrelevant. It just has to be faithful and transmit the message. But the message should be encoded in a way so that the eavesdropper, who's called Eve in this standard cryptographic story, can't, from what Eve sees, is able to detect, she can't infer the meaning of the original message M, because she does not know the nature of the key. Now, when this gets to Bob, this is the beauty of the protocol. It's symmetric. So Bob gets the ciphertext, He has a copy of the key by previous arrangement with Alice. And though he just has to do the exclusive OR of the ciphertext with the key to recover the message. It's very beautiful because it's so efficient, and you do the same operation done in reverse, takes this meaningless message and reproduces it on the other end in a way that can be made secure from an eavesdropper. So this is, in the theory of communications, there's several things that you have to worry about. One is the making the communications medium opaque by just injecting so much noise into the medium that no transmission of information is possible. But that's rarely required. And the other is to keep the communications medium secure, so that in fact, and in order to be economical, it should have the widest reach. So you want something where everybody can read what's written in the medium, but only the sender and the recipient can interpret the message with confidence because they have the shared key. So Vernam got this patent that is shown in the previous slide, and there was a demonstration of the Vernam cipher over the public telegraph system. Here's a correspondence between the American Telephone and Telegraph Company. And what was done was there was a message that was punched on paper tape, and there was a key. And then you could use the paper tape, the paper tape message and the paper tape key in a telegraph system to have high-speed encryption and decryption. It's an amazing coalescence of ideas. Paper tape. Have any of you used punched paper tape?
I did a long time ago, very long time.
Yeah, me too. Well, can you remember ticker tape parades? Here's one that occurred in Chicago in August 1969. Welcomes the Apollo 11 astronauts. And this looks to me like LaSalle Street. Does anyone there in Chicago can they confirm that? Anyway, LaSalle Street was as I recall, a place where a lot of banks and stockbrokers were. And they used this paper tape for messaging and for transmission of stock prices. And in these grand parades, the guests of honor would parade down the street, and then spools of this paper tape would be thrown out of windows. I guess you have to be really old to remember stuff like this. And this paper tape, I actually, during my first extended stay in the Chicago area, I was working at Argonne National Laboratories. And I actually programmed computers using a machine of this type, the Teletype Model 33. It has an ASCII keyboard and a printer, but it also has an associated paper tape punch. So if you wrote code, you could have it printed out in this punched paper tape. And then if you wanted to read the code, you got done with the day, you could dump your program onto the paper tape. You come back the next morning, you could put the paper tape back through the spool, and it would reproduce the code that you'd written before. This was actually first used in the Jacquard loom in the early 19th century, a series of punched cards was used to control weaving machines to greatly improve the manufacturing of tapestries. And then there's the stock ticker was used, so that with the stock ticker was a machine connected to the public telegraph system, which would send it would be fed its information, was punched on paper tape, typically the alphabetic code of a firm and the value of its share prices and the timestamp, and that could be sent over the telegraph to another location. And then those of you who've programmed in Fortran may recognize the name of Hollerith. He took a different approach, slightly different approach, replacing the tape by a set of punched cards. He worked for the U.S. Census, and so he had an invention which had the census raw data put on punched cards, and then the punched cards could be collated and analyzed by a card reading machine. And this, the company that he founded, later became IBM. So once again, here's this very simple digital communication, zeros and ones, a punched hole or no punched hole. And then the reader would be a set of spokes that, ran over the hole, and later on, optical lights and photodetectors. So it mechanizes the production, transmission, and reception of binary information. Now here we come to, I love this illustration. It's a quarter of a century old now, but as fresh as the day it was born. So it shows in a very vivid way the transmission of an image from one location to another by use of Vernam encryption. So this is, how old is this? Okay. The message M is this digital image, 12-bit color. How many bits is the color on the current mobile phone? Anyone? Come on, you look at it every day. Someone's got to know the answer to that.
24 bits plus.
Exactly. It's 24. Even like 4K is 24 bits. And then there's some other things that are, I think they're mostly for error correction. The 24 bits is pretty much at the limit of the human visual system. So this 24-bit decision is kind of, it hasn't changed in about 20 years. Okay, so for very high-end video processing, there might be 48 bits. I think there are actually 48 bits in the cell phone camera, but the display is only 24. And the reason for having many more bits is that you can make even finer differentiations between colors, which might be important when there's many, many, many stages of processing. But 12, and by the way, what's 2 to the 12th, anyone?
4K.
Yeah, 4K. That's not a lot of, we now have the current system, 24-bit color is like 16 million, the way I calculate it. So it's not twice the color resolution. It's like 1,000 times the color resolution. Oh yeah, and a digital image of 140 by 94 pixels. Okay, so this is really this is in the early. This is when only an institute like the Los Alamos National Laboratory could afford a digital camera. So here's the original image. This is the message. And now here, do you see? It's exactly the same format that is 140 by 94 pixels, but each pixel has a random color. Okay, so Alice does the exclusive OR of the picture with the noise, and she gets another. I mean, obviously, right? If these pixels are all random colors, then any image that you put that you composite with it is also going to just consist of random colors. And there they are. She sends the ciphertext, which is this, the exclusive OR of the message and the key, to Bob. Bob takes this message, which just looks like noise, does the exclusive OR with his copy of the identical key, and lo and behold, like magic, the image is reproduced with full fidelity because it is a 12-bit color digital image. Oh, okay. So back to the electrical telegraph. That was killed by radio telephony, but it's since been resurrected in an unbelievable way. So here's a recent diagram of all the submerged optical fiber circuits worldwide. It's maintained by this telegeography business intelligence agency. It reports that there are 1.5 million kilometers of submarine fiber channels worldwide, attached to every continent. I guess Antarctica's left out. There's not a lot of inhabitants there. That's twice the distance between the Earth and the Moon. So this shows, just indication, the massive investment in modern networks. And this is just for the undersea traffic. Then the land traffic is something equally, is even more significant. Okay, now, here's I want to read an excerpt from a just absolutely wonderful book I recommend to everyone, Mathematics and Computation by Avi Vigdasson, a very eminent mathematician at Princeton University. And this book is available in print from Princeton University Press, but Professor Vidgerson maintains a free PDF download on his website. So I'm just going to read, I paraphrased these 3 paragraphs from his input. So, how is this a theory revolutioning technology and science? Numerous human activities require secure secrecy. Personal diary files, data, financial instruments, bank accounts, stocks and bonds, voting. You want to be able to vote, or in our society, you're entitled to a secret and secure vote. You want to have, for legitimate reasons, very private conversations that have direct conversation with another party or a small group of party, and there need be nothing surreptitious or evil about it, but you just want to have, for any number of reasons, confidential conversation. Competitive bidding. You want to bid in an auction without revealing your bid to other bidders in detail. There's a legitimate reason for doing that. Or just playing games. Playing a game of poker or hearts is innocent form of enjoyment. And the whole thrill of the game is that only certain of its movement, or bridge, for example, only certain of its movements are known to all players. But then from those, other players have to make their own decisions, et cetera, et cetera. So for all these, this describes much of life when you think about it. And up to the very recent present, those activities were secured with physical means. Playing cards, which are, on one side, they just have a pattern and you reveal the card, whether it's the ace of spades or the nine of hearts, that's printed on the other side. Sealed envelopes, supervised ballot stations, locks and safes, banknotes and ID cards, very common in society for strictly legitimate purposes. They can also be exploited illegitimately. So the goal that was taken by the computer scientists was to be able to replace all these physical objects by information bits. You might wonder how that is possible at all. And here's a direct quote from this book. Despite or because of these severe limitations, these seemingly impossible ambitions were found to be possible through the theory of modern cryptography. The confidence to ask for the moon evolved for about a decade from the late 1970s to the late 1980s, when successively varied and more difficult tasks were found possible in the new framework. It should be stressed that these developments happened before the internet arrived on the scene. Moreover, this theory enabled e-commerce applications on the internet, motivating its rapid expansion through private companies' investments. This is an incredible story. Conclusion: modern cryptography is one great example of the incredible economic consequences of curiosity-driven theoretical research. And the prevailing mode, the way this is implemented now is called public key infrastructure. There are many aspects to it, but a good iconic example, so-called RSA, Rivest, Shamir, Adelman encryption, where you use, and this is something that's used for digital signatures, and other things very similar to this approach are used for, all of cybersecurity now. There's a patent. It's part of the national public key infrastructure. And the way it works is that when you exchange information with a counterparty, you send them your public encryption key, so they can use your public encryption key to decode their answer, and they send their answer back to you, and you can decrypt it on your private decryption key. So you publish a secret key that can be used by anyone who wishes to communicate with you, but you don't publish the decryption key. And the reason that this works is that because it's key from the encryption. In other words, knowing the encryption key does not give you convenient information for inferring the decryption key. Let's see if I've got, so here's, and the difficulty can be described in terms of finding the prime integer factors of a number, which you can easily for small numbers you can easily find the prime factors just by brute force computation. But when you go to very large numbers, so far there's no standard computational algorithm that can find prime factors efficiently. So, for example, you can find on the internet this RSA is Rivest, Shamir, Adelman published some large numbers as a challenge, and as of today, I think it's still today where I am, the largest publicly known factored RSA number has 829 bits, which is 250 decimal digits. It was published in 1991, factored in 2020. There's a Wikipedia page on these RSA numbers, and you can see there's many larger ones also haven't been factored or not knowingly been factored. And so the whole purpose of this approach is that it's so much easier to create these large numbers than it is to factor them. So if you say if all the computers in the world can just break this RSA number of 829 bits, if you just add another 30 bits, you go to a number with 859 bits, it would make it 1,000 times harder to break. So, computer technology advances quite rapidly, but by having an encryption standard that also keeps using a longer and longer number, you can keep, I would say, the older information will eventually be decrypted because of advances in computer technology, but most of that old information is of time-limited value. So you can always, for things that really need encryption, like even personal medical data, right, which might have a 100-year lifetime, you can easily assure that will by changing encryption standards over time, the encryptor can keep pace with the decryptor. Now, all that changed in theory in 1994 by Peter Shor, who showed that the finding prime factors of an integer could be done efficiently with a hypothetical quantum computer, which had not been demonstrated at that time. But that the possibility of it means that many people started to become concerned. Yeah, and here's an example from a paper by George Mosca, 2019. Factoring a 2048-bit integer with a quantum computer with these type of specifications, and nothing like this exists right now. But there's rapid progress in experimental quantum computing. Would take a order of a day. So that the fact that a quantum computer might be built has caused new attention to be given to the long-term future of data security. So one procedure is the use of quantum cryptography. So you use quantum mechanics to the quantum mechanics is not used to encode a message, but it's used to develop two copies of a secret key by remote communication between two parties, and to do so in a way that is secure against eavesdropping. So this relies on the in this here's an example published in Nature, June 9, 2020. It's by a group in China. Zhangwei Pan is the leader of that group. Arthur Eckert is the inventor of entangled photon quantum cryptography. And many of you can actually read much of this paper with understanding. A good way of starting to learn about this technology is to look at the circuit diagrams, right? And then figure out what each one of these acronyms means. It describes the how the photons are generated and detected. And if you do that, you can possibly get a very good practical sense of how these keys are generated. In this case, what's done is there's a pair of photons that's created by a laser circuit within this low Earth orbit satellite. One of those photons, elementary particle of light, is sent to a ground station, and the other is sent to another ground station 1,000 kilometers distant. And so by a process of communications between these ground stations regarding the photons that they received, they can develop a secret key to use in one of these cryptographic protocols. Now, another paper by the same group describes the incredible national network that uses this photon-based quantum key distribution to provide secure key for long distance for sensitive communications along a network that runs from Beijing to Shanghai. Very impressive, high investment opportunity. This is now approaching, being 4 years old. And the significance of this to me is this is an illustration from the paper. This is a large quantum communications network, much larger than any network we know in any other country. And what's its purpose? Well, it's illustrated by this diagram from the paper. In any network, there's an application layer. Say there's, a consumer walks into a bank office and wants to transmit money to another bank account. A buyer wants to transmit money to the bank account of the seller. So buyer goes in the bank, tells the clerk what they want to do. Then the clerk communicates that message down to what we call the classical logical layer. Say, send money from this address to such and such address means you have to write code that describes that action in a way that can be interpreted by the physical layer of the network. So the human instructions are converted to code, and the code is sent to machines that execute them. And then on the other side of the transaction, you have the reverse. The receiving machine receives a signal from a digital signal from the network that's converted into logical instructions of what action is to be taken. And those are communicated back to the counterparty application layer for actual tendering. This is how all electronic commerce works. Now, when you're implementing a quantum network where it has this quantum encryption that's going on, or other quantum enabled actions, you're always going to have the classical layers present, because the whole purpose of the investment is to get real results in the real world. That is, to transmit human desires into human actions. So you're going to need, but everything can be accomplished quite efficiently by the classical layers. But if quantum is needed for an extra layer of security, then you're going to need the corresponding quantum logical layer and the quantum physical layer. And the point I'm making here is that there is going to be, if this is important, there's going to be a huge advantage to entities that can experiment with this new type of network architecture on a large scale. And China is very active in doing that.
Excuse me, I have a question.
Yes.
So does that mean that quantum computing, as far as this goes, it operates on the lower levels of the TCP/IP network framework?
Yes, that's correct. So this is something that I assume that you're sort of familiar with in principle,
Yes,
right? The
in
classical
principle.
logical layer is like standard code, and then converting, and the conversion into the the bit structure is done at the, and the logical elements within the physical layer. And so
Okay.
if there's to be an effective quantum modality, you might say that maybe this application layer would have a separate well, it probably won't have completely separate communications with the classical layers and the quantum layers. There'll probably be a necessary interconnect between the quantum layer and the classical physical layer, because it's at the physical layer where you're going to start to use these tricks of quantum mechanics to make the information that you send on the physical layer secure.
Okay, so the network layer is still pretty classical as well. But
Yes, that's right. That's right.
Okay. I thank
Yeah,
you.
so it's not to do something. These are not being built to do something that's impossible to do by the classical layers alone, but it's to enable, for example, if you want a much higher degree of security, then you can use the quantum logical and physical layers to transmit the information in a way that is very, very difficult to decrypt
Now,
by classical attack.
isn't the quantum physical layer when we transmit? So we start at the top. When we have to transmit essentially qubit states
Affirmative.
from Alice to Bob.
Yes.
That transmission, that's not going to be ordinary TCP/IP.
No. In fact, this is my laser pointing showing up here. Here's that satellite using this entangled photon communication between two ground stations. So this is an example of the quantum physical layer that's being used to provide an encryption, a shared encryption key for two ground stations, and it's using parametric down conversion, classic quantum optics, a well-known, iconic quantum optics phenomenon where you put one photon in and get two photons out, and those two photons are correlated in such a way that it can be used to make a shared encryption, a secret encryption key that's shared between these two counterparties. But then also some of these nodes here are connected by optical fiber. Actually, probably there's multiple optical fibers connecting. So it's part of that fiber is just standard optical fiber. And then another part uses a different type of correlated photon generation to make the there's a quantum channel in the fiber, parallel dark fiber, that carries that's used to transmit the shared secret key. I actually encourage those who are interested, I encourage you to take note to look up these papers. I think they're actually freely available online, in my opinion, they're very clearly written. And as I mentioned, you can learn, if you want to, like start really reading technical literature, one of the best ways to do it, in my opinion, is to look at these circuit diagrams like this, and at least make a list of what everything means and a short description of the function that it performs. And in fact, the underlying ideas are quite simple, but they have to be implemented in physics that's it's quantum physics, and there are some simple aspects to it, but a little bit of familiarity with it will actually give you good insight. And I'll get into some of that in the final section, which is, well, I just want to say one sort of recent advice. So the National Security Agency has been keenly observing the evolution of quantum cryptography, and has made some recommendations. And there's a national investment in the development of so-called quantum resistant algorithms, which are not known to be susceptible to quantum attack. And let's see. So there was an 8-year-long project at the National Institute of Standards and Technology and the Computer Security Center to develop federal information processing standards for so-called post-quantum cryptography. So it's to develop standards that are not known to be subject to quantum attack. So it's taken a long time to do this. And if you work in information technology, you should know that these are, we have an existing cybersecurity infrastructure. The intent is that that's going to be replaced in computers, in all computers used by the U.S. government over the course of time, probably a decade. But when the inevitable result is that the entire world, well, this is my prediction, the entire world is also going to have to move to these post-quantum cryptography standards, because no major manufacturer is going to build a highly capable computer that cannot be sold to the federal government, which is such a big customer. That's certainly what happened before. So you might want to ask your CIO if your firm is looking into these post-quantum cryptography standards, because they've just come out, and I believe that they'll be the focus of considerable activity in IT security. Okay, I'm going to conclude with a couple of quantum examples. So we talked about the two-photon two-photon, these production of two photons. Okay, so let's look at a property of the photon that you've seen every day in your life. It's dark where I am right now, and I'm looking out the window of my house, and I can see into a house which is about I guess it's about 100 meters away. There's a room in that house, and the lights are on, and I can see with my eyes that there are people in that room. I can't make out the features, but what's going on there is the light in that room is coming out of that window, and it's coming into my window about, well, maybe it's 60 meters away. And if I turn off the light in my room, if I turn off, which I just did, I have great confidence that the people in that lit room that I'm looking into can't see me because there's no light, or there's very low level of light coming from my room. And this is does anyone here watch these police shows? The standard element in the police drama is a suspect is being interrogated in a room with a one-way mirror. Am I right? Nobody's seen any of these cop shows?
I don't normally.
Just on TV.
Yeah,
Yeah, on TV. But you've seen this stuff on TV, right? Or in the movies.
all the time, right? Even though I don't watch many cop shows.
Yeah, you can't avoid it. And I'm sorry for spoiling you with this, but not that sorry. So I'm going to ask someone, tell me how a one-way mirror works. Make up a story of how a one-way mirror works. There's a clue in the
I'll go
image,
ahead.
on the image to the left, which is a photograph by the art photographer Wolfgang Tillmans.
Maybe there's some sort of material in the one-way mirror that doesn't allow the light to reflect through it.
Yeah.
The light in the observing room is it's dark in the observing room.
Yeah.
Or the light level's way lower in the observing room than the
that second answer it is so perceptive because there aren't that many non-reciprocal optical materials, and glass is not one of them. But all you have to do, and by the way, if you watch the cop shows, that's the way it works. You just have a very bright light in this room, and the room behind it just has a low level of light. So as the light in this room is actually escaping through the glass pane into the room where the perp is being, or the suspect is being interrogated, but it is so dim that it can't be seen by them. And for glass, we know what the answer is. If you send light at a glass window, about 8% of it will be reflected. Now look at this lovely picture. There's the subject here is in a room looking out. This is the picture in its entirety. Okay, I haven't clipped it at all. Well, we can see that it's a clear day outside. Light is coming in from the window. And we know that because do you see the light on this wall, which is blocked from the window? It's darker. And then here, it's lighter here because there's light coming through the window from a clear day. And now look, the subject has her hand placed on the window. And you see this reflection. Tell me where that reflection comes from.
The light inside her house. Most
Oh,
likely,
does it?
right?
The glass is refracting.
Oh, does it? Wait, okay, tell me where tell me where this reflection of her hand comes from.
The glass is refracting the light back into the room.
Yes. You can
Yeah.
see the glass is emitting a lot of light, okay? It's emitting light that strikes her hand, but then part of that light is reflected back, and you can see the reflection of her hand in the glass. This, when you look at this from the quantum level, it becomes a profound mystery. Okay, so here's the standard figure of merit. I mean, it's different for different glasses, but it's about right. About 8% of the light incident on glass is reflected. Okay, so what quantum mechanics tells us is that light, well, this is a sort of a simplified version, but the simplified version is very well down. Light is made of individual photons. They're elementary particles of light that can't be subdivided. So when you think about it from this standpoint, there's a huge shower of photons coming through this window. The numbers are enormous. When a photon, which is created in the sun, by the way, it comes to this window. Well, we know that 8% of the in a one-way passage, 4% of the photons will pass through the window. So 96% will pass, the photons from the sun will pass through the window, and 4% won't. But since they're all identical, which 4 photons, say you have 100 photons in a pulse, which 4 know that they have to be reflected? Well, quantum theory just says it's indeterminate. Just there's a probability that it happens that way, and that is validated by experiment. But what this means from the standpoint of what our eyes see a low level of light, low intensity of light that's reflected from the window, and a high value that's transmitted. But what's actually happening is we have these single photon events, and most are transmitted, but every once in a while they're reflected. And quantum mechanics tells us, and experiments show it, that this process is intrinsically random. This is a very shocking thing for physicists who are used to, they're supposed to be dealing with certainties. To find that there's an intrinsic random element in nature seems like a big mistake. In fact, Einstein himself, in a latent life, rejected the quantum theory as an expression of reality. Well, so I'm going to let's see. I think I'm sort of running out of time here. Let me just say that this is if anyone wants to get a copy of these slides, they can contact me through the organizers. There's a iconic, the best, if you want to understand quantum technology, my advice is to go study a quantum random number generator. That's a device with an important function. And here's a circuit diagram of a really ingenious device of that type, quantum random number generator, which just contains an LED light source, a prism, 2 detectors, and some counting electronics to generate digital numbers that are intrinsically random. Very beautiful, very well written, and basically it sort and almost self-calibrating. So the way that you get to the quantum regime is you want to use, in this case, you use a light source that's sufficiently weak that at any given time there's going to be no more than 1 photon. This optical circuit is just a let me see. How do I get a The optical circuit, it could just be a polarizing beam. It's just a glass cube. Well, a fancy glass cube. You have a LED, so the intensity light is determined by the voltage on the LED. You turn the voltage on the source, and you have these two detectors. So what's produced here is a beam splitter. When a single photon comes into this, it'll either be sent to D1 and trigger a count in that channel, or to D2 and trigger a count in that channel. So you just turn down the voltage of the detector so that there's almost never that you almost always get either a count in D1 or a count in D2, but you never get a count in both channels. Because if you get a count in both channels, that means there are two photons present. One is sent to one, one is sent to the other. So sort of self-calibrating, you can get into that same photon. And this is, here is the Alibaba Cloud Intelligence Business Group was developing quantum random number cloud platforms about 4 years ago. And using a large number of exclusive ORs of messages in order to get the highest level of security. So you can see some of these elementary things are just keep carried along in the development technology. Here's a more complex circuit from that paper. And there are now some commercial devices on the market that generate quantum random numbers for a variety of applications, cryptography, gaming, pin number generation, numerical simulations, etc. In fact, there's I think it's a Samsung mobile phone available only in Korea, as far as I know, that has a quantum random number generator in it for just this type of activity. And I'll just conclude that there's another one particularly important use of random number generators is for the production of data security primitives. And that's becoming of a concern with the proliferation of the Internet of Things, these low level, low power, low computational capacity devices, like your doorbell, right? You have an Apple doorbell, right? It's like internet connected. They don't have the power that is going to be needed for post-quantum cryptography. So there's, an evolving challenge of figuring out how we're going to develop, computationally efficient techniques that can be handled by low capacity devices that will guarantee security. And this is a very informative article by James Hughes and Whitfield Diffie, who's one of the founders of IT security, available online. So I think that comes to the end of my presentation, and I will often respond to email directed to me at this address. Very simple. It's the simplest email address I have, cwc@umd, that's University of Maryland.edu. Or I suppose that, if you contact the organizers, they'd be willing to pass things on.
Charles, are you on LinkedIn by any chance?
I am. Charles Winthrop Clark.
Everything spelled out?
Yes, the middle name is Winthrop, Winthrop.
Okay.
But if you use Charles W. Clark, you'll probably find me there.
Okay.
Okay, thank you, Charles. Do we have some time for questions, or are there any questions out there?
I have a quick question. Did I see a slide go by quickly that you didn't talk about that had the title, government says QDK is deprecated?
Yes,
I saw
QKD,
that too.
QKD, and
yes.
that's correct. I skipped over that, but I can. Let's see. Let's look at that slide. So you can certainly let's see. This
So
is quantum. That's not the. Yeah. So you can
Here it is.
find this. This is a public document. I downloaded it from the internet, issued by the National Security Agency, and it says NSA continues to evaluate the use of cryptography solutions to secure, et cetera, in national security systems. NSA does not recommend the usage of quantum key distribution and quantum cryptography for securing the transmission of data in national security systems unless the limitations below are overcome. And this is a fairly short document. You can read what those limitations are.
Yeah, the main limitation is the technology. I mean, it's been demonstrated, but it takes a long time to move a quantum generated key from point A to
Yes.
point B, and the throughput isn't there to keep up with the massive amount of
Yes.
data that has to go
Yeah.
through.
I'm not criticizing the NSA for this and from this analysis at all. In fact, it's kind of like we have a nice physics trick that works in a laboratory environment. But once again, this is another reason, I will say, for sort of the national security implications of the existence of a QKD network, which this is. So they're going to discover much more about the real implementation security issues than someone with just a transmitter and a receiver on a laboratory bench. I mean, the real practical problems of quantum key distribution are going to be revealed on a complex network with accumulation of large statistics and so on. So I think that is a reason for, even though at present, the NSA does not recommend the usage of quantum key distribution in national security systems, there's certainly a very good reason for trying to understand the implementations of a real world network that use quantum key distribution. And our international competitors are, as I see them, are investing a lot of money in that enterprise.
Okay. There always seems to be a lot of confusion when this topic comes up, specifically, and it has to do with the terminology, the unfortunate vocabulary of quantum, where they try to use words that are connected to the classical world or whatever, and they don't mean the same thing. A quantum network that will evolve won't be like a classical network. It is, as far as what I've seen, there is no quantum equivalent of a TCP IP layer at the moment. I mean, if you think about it, if you create a qubit as a photon as a qubit, and you can send a single photon over a fiber, that's great. But how do you bundle a bunch of them in a packet? All of the mechanics for packet management kind of start failing.
That's right.
Because once
right.
There's no air, there's no way to you can't tattoo a photon to find out what packet it belongs to, et cetera, and stuff like that. So these networks, and you did say it a couple times. It's a quantum key distribution network, but sometimes the QKD gets dropped, and people just think, oh, there'll be a quantum network, and
Yeah.
it'll be really fast. And no, we're not. We're
Yeah.
miles
Well,
away from
so yeah, I mean, so the most of the so-called magic of quantum mechanics comes from the fact that there's no known way. It's theoretically impossible to duplicate an unknown quantum state. You can't create a
right.
copy of an unknown quantum state.
Yeah, the no cloning theorem.
The no cloning theorem.
Yeah.
Whereas with, in a classical system, you can just, it's very easy to replicate a signal.
Right.
Now, there is a modality that enables transmission of quantum states, the so-called quantum repeater. But that's still kind of so the quantum repeater takes in an unknown quantum state and outputs the same unknown quantum state, which is
right.
what you would really want for a working quantum network.
But it does it by destroying the origin.
Well, it requires it requires it requires something that doesn't make a copy, but it requires a process of transformation so that the output is the same as the input without the state being actually measured. So there's still the same intrinsic uncertainty. And that there are theoretical prescriptions for doing that. And there's a lot of experimental work on developing quantum repeaters. But it's basically very similar to the process of quantum error correction, which is a way of another astonishing thing that I'm not the person to discuss. I wouldn't have the time to do so if I were. But that's again something whereby you have some other ancillary qubits that can be used to pass the core of the important quantum core of the state law, to replicate it again and sort of extend its life without actually making a purely destructive measure.
Yeah. So quantum key distribution is one thing. Post-quantum cryptography is actually another thing. They are kind of related, but they are two different things.
Completely. Post-quantum cryptography is a purely classical
problem,
process, and it can be implemented today. In fact, the way that this competition proceeded was that basically different teams went back into history and looked at encryption algorithms that weren't popular and tried to see whether a convincing case could be made that they were not susceptible to a factoring attack.
Okay.
And there's been a consensus on something called lattice systems.
Yeah.
It
seems like
they're not known to be subject to quantum attack.
It seems like the hope was QKD would help out a lot because it would enable symmetric key systems, which are by nature a little bit more quantum resistant. So that's why, and NIST is saying, that would be great, but the technology isn't there to have with the throughput plus the range. There are some QKD networks in the US, but they're like 10, 12 kilometers long, and that's it. That's what they get out of them. But the third part of this thing is quantum cryptography, where the quantum itself is involved with cryptography. I haven't seen much on that. So my question to you is are there any new developments in that area where a quantum computer actually participates in the cryptology, in the encryption, and it's not anything related to QKD. It's not related to the teleportation algorithm. It's some other method. I haven't seen anything really happen on that. I've seen a couple papers go by, but they're
Yeah,
very
I don't have any
incisive.
familiarity with
Yeah,
that literature. I
yeah,
mean, my main interest personally is like what's being deployed. And
yeah.
so yeah, because like what are let's try to put some really hard bounds. I think it's worth an investment in QKD research to figure out what the really hard how to ameliorate the hardest problems. What are the potentials?
Yeah.
Because there's a very solid theoretical foundation of it, and it also it keeps on coming up with new twists as optical technology develops. For use of entangled photon pairs is kind of a new development in that area, and it's being subject to implementation.
Okay,
So,
very good. Go ahead.
before we hop off, so my main question is, I learned a lot. So basically, it all comes down to how well humans can come to manipulate light, photons themselves, and how well they can control it.
Yeah, for the things for the what the examples I showed are mostly from quantum communication. And yes, I mean, light, light is, let's say, there are some possibilities for using quantum phenomena in other modalities for quantum communication. But optics is the best thing we've got. I mean, there's this 1.4 million kilometers of optical fiber. It's so great. It's the best communication medium that we have. So from a practical perspective, it seems to me that you start by seeing how quantum techniques could improve on the best that we have. Now, if you say, okay, we want to look at quantum acoustic community, you do something with to introduce quantum security in sound waves. I mean, that might be a very rewarding scientific subject, but it's not leveraging the best available technology for communications.
Okay.
I mean, if you look at the modern mobile phone, that's something just nothing like it was known 40 years ago. It's
Right.
so radical. I think it's the greatest invention we've known
I
in our
agree. Yeah.
lives in terms of its complexity, capability, and how much it differs from its ancestors. And it's been made possible by the confluence of many streams of advanced technology, semiconductors, antenna design, photoelectric cells, sensors.
Hmm. Speaking of semiconductors, I are you up to date with like the FANG companies? I heard that Microsoft came out with something called a topo conductor, and it's supposed to help them compute qubits. It's supposed to replace the semiconductor. What do you guys think about that?
So, I mean, that's a paper came out, was published just in the past, I think about 2 or 3 weeks, by a Microsoft research group on using something called a Majorana.
Particle.
It's a type of excitation in a semiconductor, which has promises for being used as a qubit.
And
And
it's based on
research,
those Majorana particles, which go in and out of existence. And lots of physicists who have read that Microsoft paper aren't convinced that Microsoft has trapped one.
yeah. For example, there was a paper by another group that was being supported by Microsoft, looking at this Majorana phenomenon that was published, I think, in Science magazine about 2.5 years ago, maybe 3 years ago, and that paper was eventually retracted because of errors. So I think the condensed matter physics people that I know tell me that Microsoft has really outstanding experimental capabilities, and they've hired a lot of very good physicists. In fact, I know one of them. But this is a research paper, and it hasn't, there's no consensus that it's actually demonstrated the Majorana particle that it presents evidence. I think it's a serious scientific effort. It shouldn't be dismissed, but it's not like the smoking gun has yet been found.
So the great hope of the Majorana, of Microsoft's supposed invention, is that you can, if in fact you can trap that particle, which again a lot of people aren't convinced they've done, because it's a particle that was just discovered recently, or I mean, when I say recently in physics, like at CERN or something like that. It goes in and out of existence, which just blows your mind. But the great hope is, assuming you could trap this particle, it can be manipulated with simple voltages, as opposed to other qubit technology, which takes like elaborate lasers or microwave channels or all sorts of other things, and the supporting infrastructure for a single qubit, the overhead is crazy. Whereas these things, if they can make them do what they're talking about, it's basically just like a transistor. Send it a little voltage or set a voltage on it, and you can manipulate it. But I think I wouldn't hold your breath at the moment. I mean, there's a long ways that they would have to go, I would think.
All right, yeah. Thank y'all for that insight. I'm also an investor, so I'm very on to that type of information. So okay, that's interesting though. So really Microsoft, they kind of just tried to pull a corporate stunt, try to
Well,
not
I
even
think
like
that I wouldn't
yeah.
characterize it like that way. That
No.
Microsoft has invested in a very high quality research group, and
Yeah.
they've spent a lot of money on this quest for the Majorana particle. I think it probably started 20 years ago, and they have some brilliant people working on it. And so, I think it's kind of it's a company the size of Microsoft can well, let's say the transistor. Okay, where did the transistor come from? Well, it was invented in Bell Labs. If you look at the first transistor, it's about the size of my fist, right? And it does this one looks like a piece of junk that was put together. Now you get, you know, a billion of them on a chip. So it sometimes, you you start with an invention, and it turns out to have, it turns out you can scale it down. You can scale it in an incredible way. So who knows where the Majorana, I say the probability of any one single experiment yielding a revolutionary result is always low. But you can't just keep looking under the street lamp for the car keys. Just because there's plenty of light, if the car keys aren't there, you're not going to find them.
Okay. I think we're actually right out 2 hours. I'd like to thank everybody for coming. I think it's time to wrap it up, and you can reach out to any of the organizers on the meetup group, Quantum Computing Chicago, Illinois, and beyond. You can send a message to any of the organizers with your questions, or just post a message in this event's message space. And going forward, I think I believe, Barry, you have another
We have a meeting on April 20th. Keep your eye on the meetup page for details.
Okay. And just want to let everybody know if there's a topic that you're interested in, reach out to one of the organizers and let us know. Can't guarantee that we'll find somebody that can talk about it, but you
We'll
never
find
know.
somebody who makes something up.
Yeah, we'll. And if there's any people out there who want to give a talk, even if you've never done it before, I highly recommend you give it a shot. So with that, I'll call it a night. Thank you, Barry, for doing the Zoom.
Ron, you and Barry are the organizers. Is that correct?
Yes.
Okay.
We're two of the organizers. And so just again, you can post a message on the meetup site. I'm also on LinkedIn. I'm Ron Schreiner, Schreiner. You can send me a message over there, but it's probably better on the meetup site. So, all right. Thank you, everyone.
All right. Thanks for showing up.
This has been a good session. Thank you so much.
Thank you and good night.
Good night.